In this section, we'll be taking a look at the EVPN concepts objective of the JNCIP SP exam. For more detailed coverage of this topic, please check out the Juniper courses AJSPR, JL2V and JL3V.
In this video and coming videos, we're going to take a look at EVPN, or Ethernet Virtual Private Network. And EVPN provides much the same kind of service as VPLS does. We're providing a virtual broadcast segment to multiple customer sites that are interconnected to our service provider environment. So if EVPN is providing much the same services, why was this protocol invented? Why is it needed? Well, VPLS has a number of limitations. As our PEs are learning the location of our connected hosts, there's a large amount of unknown unicast flooding going on in the core of the network, which is sometimes undesirable. Also, with VPLS, it is possible to support resiliency and multi-homing, although this functionality can sometimes be somewhat brittle, so better solutions for multi-homing are needed. And finally, VPLS is fundamentally tied to MPLS switching in the core of the network for data transfer. So these three reasons meant that it was desirable to develop a new protocol to support Ethernet virtual networks within a service provider environment. And that protocol is EVPN. EVPN supports the advertisement of MAC addresses from PE to PE, which gets rid of a large amount of the unknown unicast flooding. It has multi-homing techniques built in, which we'll examine in more detail later, which means that it is significantly easier to deploy multi-homing techniques within EVPN. And it also supports different underlying data transfer mechanisms, such as VXLAN. So you can see that EVPN addresses these shortcomings of VPLS. And in the coming videos, we'll take a look at how EVPN operates in more detail. So EVPN uses multi-protocol BGP, much like we do with some of the other layer 2 signaling technologies. However, we are now using a different address family. We're using AFI, SAFI 2570. And within this address family, within this NLRI, we have 5 different route types. Each of these different route types serves a different purpose. So type 1 is Ethernet auto discovery, and this, along with type 4, Ethernet segment route, we are facilitating multi-homing in an EVPN environment. The type 2 route is a MAC advertisement route, and this happens whenever a PE learns the location of a MAC address. It will advertise that MAC address to remote PEs. We have the multicast route, and this is used to build multicast forwarding trees in the network so that we can send the broadcast, unknown unicast, and multicast traffic necessary to deploy an Ethernet multi-access segment. And then finally, we have the IP prefix route. And we'll cover these different route types in more detail in the following videos. In this video, we're going to take a look at frame forwarding within EVPN. So from the service provider's perspective, if you think about layer 2 virtual circuits, layer 2 VPNs, the service provider is acting as a hub. There's no MAC address learning going on at all. The frames are just being forwarded from one end of the virtual circuit to the other end, and vice versa. Again, from the service provider's perspective, if you're thinking about VPLS, each of the PEs is acting independently as a learning bridge. MAC addresses are being seen, they're being associated with the incoming interface, and they're being flooded out. And all of the PEs are doing this independently. When it comes to EVPN, from the service provider's perspective, we can think of all of the PEs as acting as one coordinated, distributed learning bridge. That is, a PE learns about the location of a MAC address through its arrival on a particular CE interface, and he then notifies all of the other PEs that are participating in this particular EVPN about the location of that MAC address. Thereby, we're reducing the amount of unknown unicast flooding that's going on in the core of the network. So let's now talk through the signaling that's supporting this, and we can finish by actually walking through what happens when two hosts connected to an EVPN start to communicate. So as we've mentioned previously, we have a new address family in multi-protocol BGP that's supporting EVPN. This is using AFI-SAFI 2570. And within this address family, within this NLRI, we have these 5 different route types. When it comes to signaling the location of MAC addresses and supporting data forwarding within an EVPN, we're talking about the type 2 route and the type 3 route. So the type 2 route is what's advertising the location of MAC addresses. So say we have this network here. PE1 has seen the source MAC address of host A coming across this CE interface. So he knows that host A is located behind this interface. To advertise the location of this MAC address to the rest of the network, he uses the MAC advertisement route, the type 2 route, to advertise this MAC address to the rest of the network. And then, as soon as other pieces of the network receive traffic destined for MAC address A, they can send that unicast over effectively a virtual circuit to PE1 for onwards forwarding to host A. However, when hosts join the network for the first time, there is still going to need to be a small amount of unknown unicast flooding. And we also need to carry broadcast and multicast traffic within our network. So this is where the multicast route, the type 3 route, comes in. So within an EVPN, every host within the network announces a type 3 route. So every PE in the EVPN is aware of every other PE. And this allows PEs to then build multicast trees to all other participating PEs within that EVPN, as illustrated by this orange link here. PE1 has a multicast tree built to PE2 and PE3. So that allows PE1 to flood traffic to all other destinations within the EVPN. On Juniper devices, currently only ingress replication is supported for the distribution of traffic to the multiple different endpoints from the ingress PE. So we've talked about that we have these 2 different route types that we're using to build our unicast and multicast forwarding paths. Let's now walk through a scenario where, say, host A and host B interconnect to this network for the first time. Let's see how these facilitate traffic forwarding between them. So host A connects, and host A sends traffic to host B via CE1. The frame arrives on PE1. As we've mentioned, PE1 builds the MAC address forwarding table associating the source MAC address with the incoming interface. PE1 does not know the location of destination MAC address for the host B. So he uses the multicast tree to flood this frame to unknown unicast flood to all other PEs. And there's flooding going on on the local switch as well, that frame eventually arrives at host B. As well as this flooding going on, PE1 has used a type 2 route to advertise MAC address A to the rest of the network. Host B is now likely going to reply to host A. He can do this immediately via unicast because we have the MAC address learnt from the type 2 route advertised by PE1. So host B sends traffic to host A across CE3 to PE3. PE3 learns the location of the MAC address B, associates it with his incoming interface, and also advertises the location of that MAC address in a type 2 route to the rest of the network, as well as forwarding that packet along the unicast path to PE1. If host A was sending broadcast or multicast traffic, PE1 would just use the T3 announced multicast tree for forwarding indefinitely. And thereby you can see how EVPN can support traffic forwarding between different connected hosts for different types of traffic. Now let's take a look at multi-homing for resiliency within EVPN. So if the network knows the destination MAC address of the frame, it's been learnt previously, then you can think of forwarding traffic within EVPN exactly the same as you would think of forwarding traffic within a L3 VPN environment. And this holds true for single-homed and multi-homed destinations. For multi-home destinations, imagine this is a layer 3 VPN. We've learnt a route from 2 locations. That route's being announced, and when we're going to be forwarding traffic to hosts that are identified by that route, we're either picking the PE closest or we're load balancing across those 2 destinations. For EVPN, when we know the destination MAC address and it's been learned by the network, the behavior is exactly the same. We're just picking the closest PE and forwarding traffic. Now, so this is fine when we have known unicast traffic. But what about if we're dealing with broadcast traffic, multicast traffic, or if we don't know the unicast MAC address? So this is where we need to build in certain measures within the protocol to deal with these scenarios. Otherwise, we could quite easily get forwarding loops. Imagine we have broadcast traffic coming from CE1. It's hitting PE1 and being ingress replicated to P2 and PE3. They're both forwarding that traffic out to CE2, who is then flooding that traffic back towards them. And we have this flooding loop then, which is obviously undesirable. So mechanisms have been designed into EVPN to deal with broadcast traffic in the situation where you have a multi-homed CE. You have a CE connected to multiple PEs. This is what we'll take a look at here. Let's examine first off traffic going from PE1 to PE2 and PE3 to host B sitting behind CE2. And to deal with these situations, what we do is that we elect a designated forwarder, and we only have one of the PEs responsible for forwarding broadcast, unknown unicast, and multicast traffic to the CE. What we do is that we configure a ESI, a Ethernet segment identifier. This is 0 when CEs are single-homed, and it is the same for all interfaces connecting to the same CE. What we then do is that we use type 4 routes that refer to this Ethernet segment identifier to elect the designated forwarder for that Ethernet segment. Thereby, only one of the PEs interconnected to the CE is going to forward broadcast traffic to it, so we're removing the chances of any kind of forwarding loop. So we've seen how electing a designated forwarder can stop switching loops when we have broadcast traffic coming from a remote PE to a destination that's multi-homed. What about when broadcast traffic is originating from within that multi-homed site? Let's turn to our diagram again. Say we have broadcast traffic incoming on PE3's interface. This traffic is going to be sent out of the multicast tree to all other remote PEs. PE2 is included in that multicast distribution tree, and PE2 is the designated forwarder for this Ethernet segment. So he's obviously going to forward that traffic back to CE2. And again, we have a switching loop that results. So obviously we need an additional mechanism in place here to deal with situations where broadcast traffic is originating from the multi-homed site. So this is how this mechanism works. So again, we have our T4 routes, our Ethernet segment routes that are announcing the Ethernet segment identifiers between multi-homed sites. In addition to this, we are also sharing T1 routes, that is Ethernet auto-discovery routes. And they have other purposes as well, but for this specific use case, they're there to facilitate split horizon. That is, only forwarding broadcast traffic when certain conditions pass. And within this T1 route advertisement, we extract a label value. And this label is appended to all frames that are received from a multi-homed CE that are sent by PEs that are not the elected designated forwarder. So in this case here, PE3 is not the designated forwarder for this Ethernet segment. So when traffic is received from CE2, when this traffic is sent into the multicast distribution tree, the label extracted from T1 is appended to the frames as they're sent. So these arrive and they get to CE1 fine. When they arrive at PE2, PE2 inspects the frames. PE2 sees the label value within those frames, and because he is the designated forwarder, he then drops them. So this prevents broadcast traffic from being received from a multi-homed site to be echoed back to that same multi-homed site, thereby preventing switching loops. And here we took a look at some of the mechanisms inbuilt in EVPN that prevent switching loops and allow us to have multi-homed topologies.